11p stack, and this 11p is a very slight adaptation to normal Wi-Fi to operate in vehicular environments. So when the Wi-Fi card is not equipped to your laptop or smartphone, but when it's equipped to your car. Okay, and this whole stuff is a bit embedded in a broader project, which I call WIME, which is for building some communications devices to experiment with wireless networks in general, so for example also with sensor networks and stuff. And yeah, since I'm a PhD student, I had to invent the problem, so this is basically my project now where I'm working on. But today I want to talk to you about this a subset, which is this 11p transceiver, which I want to tell you what it already can. And finally I want to talk about some applications. So what can you do with this thing, and maybe you find some more applications. But to start, I want to make one step back, and I don't work in software-defined radio for too long, but in the last years there were some really fast developments. So now there are very cool hardware platforms out there. We just seen the B210 from Ethos, and also the N210. There's a HEC RF and Blade RF, so that means there's now really affordable, cheap hardware, which is really powerful, also with MIMO and stuff like that. And then on the other side we have the software part, which I labeled GNU Radio because I use GNU Radio for all my stuff. And there today we already heard, for example, about Folk, which is using SIMD instruction and really speeds up the whole computation process by this vectorized instructions. And then another thing Martin just showed of this asynchronous messages, where you can really switch back and forth between stream-based and packet-based processes. So that means that you can easily implement a real communication system as opposed to just hacking in some physical layer. And yeah, and of course we have this Ofdm reference design that Martin implemented, in which are not just some blocks, but also extended the whole framework from GNU Radio. You heard about these text stream blocks, for example. And if we add this together, also all this, then we now have the tools at hand to implement some state-of-the-art communication standards. And I picked some where I know that there are some active projects for GNU Radio, which are DVB-T, which are who is really active today, then LTE, and I'm working on this Wi-Fi part. So since you have the ability to implement some state-of-the-art communication standards, and since you can really build a whole communication system, I think that software-defined radios are also now interesting, not only for this physical layer guys that are typically interested in signal processing and receiver design, but also as a computer scientist or some guy who's working on the upper layers who might be interested in implementing some protocol on top of the standards, or who might look for input data for simulations, or who is concerned about security and privacy issues of this networks. So I think that with all these improvements, that you can somehow connect these both domains with software-defined radios quite well. And today I want to show how I think you could do it with the example of vehicular networks that I talked to in the beginning. Okay, but first, just to give you a very quick idea about what vehicular networks are about. So there's this vision that cars are equipped with some radio module, and let's say that if the guy in the front car just realizes that there is a traffic jam ahead, then he has the possibility to communicate this to all the other cars around him, and the guys on the other lane could, for example, pick up this information and bring it to someone in the very back. So that means that you could make driving more safe because he's already alarmed that there is a jam and that you could maybe avoid rear-end crashes. Or on the other hand, you could make it more efficient by proposing an alternate route if you have the possibility to pick one, because he has not. And maybe you also want to include, let's say, road signs into this whole thing. And yeah, a lot of people came up with ideas what you could use these networks for, so they started to work on that and came up with a standard in 2011. And also they reserved some spectrum for exclusive use for ITS applications, so intelligent traffic systems. So and this spectrum is in the 5.9 gigahertz band. So people are actually interested in that because it's really, spectrum is scarce, you know, so to have some dedicated part of that is really valuable. And what they did is the following. They took Wi-Fi, normal Wi-Fi 11A or G, which most of your laptops are currently operating, and and just made some very slight adaptations. So what they did is they doubled all the timings. That means that your frame is stretched in time domain, but gets more narrow in frequency domain. So as opposed to 20 megahertz bandwidth where your normal Wi-Fi card will operate, it has a 10 megahertz bandwidth. From an economics point of view, this is pretty cool because you can just reuse your old Wi-Fi chip and divide the clock by 2 so that everything gets twice as slow in that case. And also from a software-defined radio point of view, that's also pretty cool because this change in timing just means you change the sample rate. And yeah, but there are some obvious problems arise with this because Wi-Fi was actually intended to operate in indoor environments like here, for example. And now if you put this Wi-Fi cards in your car when driving around on the freeway with, in Germany, maybe 400 kilometers per hour relative speed or something like that, then you don't really know what happens. And we tried to find that out, and we bought some utterly expensive hardware prototypes, and then we also took some normal Wi-Fi cards and changed a bit around in the kernel, and some cards support to change the clock rate. So with this, we could come up with some experimental devices. So these two, I have also one of those with me today. And yeah, we were driving on the freeway, and we're interested what happens when there's a truck in between these two cars, in the case, for example, and stuff like that. But all these kinds of prototypes, they have the limitation that I mean, you just get very basic data out of them. So you can send a frame, and the receiver either picks it up or not. But if it did not work, you don't know what happens. So if you're back in the lab and try to make some sense out of the data, you might easily run into problems. So yeah, so our idea was to use software-defined radios for that. And now maybe the interesting part is then I started to work on one and implement this 11P transceiver. And currently it looks like that. So I tried to build it and design it very, very layered because computer scientists are pretty used to this layered communication stack. You may know the ESO-OC stack. And there, I mean, it's there you have the hardware at the very bottom, a physical layer, then some MAC stuff, which is, for example, adding the MAC address and all that things. And then you have an interface where you can connect to, so to actually insert data into the flow graph. And it also, we already talked about hierarchical blocks today, and I also make use of them. So the whole OFDM stuff is hidden, for example, in the physical layer block. So there's an OFDM transceiver in there. And I developed this when Martin was working on his OFDM implementation. And now I obviously also want to kind of integrate this. And I already did it for the transmit side. So the transmit side is now completely using Martin's design. But the receive side, not yet. And I also have it here, and we can have a look at this if you're interested. So since you already are familiar now with Martins, it's obviously always an advantage for me if it has the very same design. So then if you then open the flow graph, then you might easily see what's going on if you're already familiar with the new radio reference design. Okay, and I created some modules to connect to that to make life a bit easier. And this is, for example, a Wireshark module, so where you can attach Wireshark and you see live what's going on. You get the frames, and you can even annotate it with bandwidth channel and stuff like that if you want. Yeah, and it runs also completely in software, so it doesn't make use of the Fpga. Okay, so at the very top you have this application, so where you can feed something into the flow graph to actually transmit it, for example. And I have an example for that, how easy that is. So with only 6 lines of Python code, you can inject a packet, for example, and send some packets out there that you can receive with your Wi-Fi card. So in that example, I used Wave Short Message Protocol, which is a protocol format standardized by IEEE, and maybe this way traffic information or also safety messages might be distributed in Vehicular Networks, and you can generate those frames and maybe distribute your own traffic information. I don't know, whatever. Really, really easily with just writing to the socket, and GNU Radio will pick that up and send out the frame. And yeah, we tried this with quite some hardware. So with all the hardware prototypes we had for 11P, and also we tried it with some Wi-Fi cards to show that this works. Okay, but then I also want to talk about the limitations of that, because this is what people ask very often. And I mean, we have the advantage of doing everything on the CPU, so it's really easy to hack, and you can play around with that pretty easy. But the disadvantage is that you add some delay. And as I said, you can connect this thing to the Linux TCP/IP stack, for example. And then the easiest thing to do is you can just ping the other device. So you connect. You just use the ping command and send some frame back and forth between the USRP and there's some normal Wi-Fi card. And here we added 100 milliseconds delay artificially, but actually that's not I know it's not a very exact way to measure delay, but the point I want to make here is about the orders of magnitude. So with this system, we are in the low millisecond scale about the delay, so around that. But if you want to meet the timings of normal Wi-Fi signals, then you have to get to the microsecond scale. So that means with this approach, you will not be able to support request to send and clear to send. This is a mechanism where you reserve the channel prior to the actual transmission, or you will not be able to send an acknowledgement in time, because there you would have to have the short interframe space, which is around 32 microseconds in that case. And then there's also a duration field that specifies some certain amount of time that you should visually block the channel, even though the actual frame is physically already gone. So this is something that I think will at least with this architecture not work, and there will not be standard compliant. But another thing that is currently still missing and that I think that we can get working is carrier sensing and channel access. And there I talked with Andre in Miami last year, and he already mentioned it today that they have an FPGA implementation for channel sensing. And he shared that with me, and we were working on that. And what we are currently doing is you can preload your Wi-Fi frame on the FPGA of the USRP, and then the USRP is doing channel sensing for you. It has an easy state machine. You can annotate, for example, slot times and all of that. And then you really can come down to the microsecond scale. In that example I plotted here, it's just the power levels. And then we had one USRP that was generating noise. Then we switched it off. And another USRP, which was sensing the channel, then added some very small gap that you would not be able to manage on the CPU. And then send out the actual Ofdm frame, and we also received this frame with another Wi-Fi card. So that works basically, but I still have some issues, basically mainly because I'm really bad in FPGA programming, and I'm currently trying to get used to. So it's not working 100% now. So having really standard compliant channel access, but I think we're on a good way. I hope we will manage that. Okay, so the last part I want to talk about some applications, and some applications from a perspective of a computer science guy, because obviously since we now have an SDR implementation, you have all the advantages, like you know everything about your signal and when it got wrong and what happened and stuff like that. But there are also some cool things I guess you can do on the upper layers, and one of those is for example fuzzing. And yeah, this is a form of penetration testing. That means you send some kind of random cluttered symbol or frame or whatever, and then you see what happens to the device driver. Actually, I did not plan to do that, but when I was working on the transmitter, then at some point I realized that it was constantly breaking the driver of my Wi-Fi card, and I had to reboot all the time, and I was pretty annoyed about that, and did not make a Git commit, because it was obviously not working. And then some month ago, I thought this was actually very cool to have this as a result. But now I'm trying to reproduce it, but it turns out not to be that easy. But I think this is something cool you might be you could do with that.
Driver that's usually assigned as a problem.
So. And then another thing is there was also some other guys in my group are working on this privacy and fingerprinting techniques. So that means that you basically want to identify a sender, want to maybe track him or disclose his identity or stuff like that. And there are approaches from this physical layer guys. They often look at channel features or some characteristics of maybe the analog front end of your device. There are some variations and stuff like that. And the computer science guys are more on the higher layers and look at traffic patterns and when did you communicate with what target, what was the packet size, or maybe look at MAC addresses and identifiers. And I think with an SDR you can get somewhere in between and try out something new, because maybe you can learn about some timings of the chip or the firmware, or maybe also the driver, because not everything, let's think of the CSMA procedure, is defined really exact in the standard. So there are always something that are implementation specific, and maybe you could use this at least as an additional information to learn something new, or to easily identify a source more robust, let's say it like that. Okay, and the last thing that we are currently working on, and where I think software-defined radios would be cool, is to enable more realistic simulations, which have absolutely nothing to do with software-defined radio. But yeah, we in our group, we also have a network simulator, which is able to simulate large-scale vehicular networks, and then you need some input for the simulator, like let's say some packet error curves, for example. And on the other side, there are some physical layer guys that were driving around with some channel sounders and have real precise measurements about and learn how the channel behaves and looks. So you have some maybe tap delay line models, or they have some coherence time, bandwidth, whatever. But you cannot plug these results directly into your simulator. You need a step in between. And I think maybe with GNU Radio and software-defined radio, you can do that. Let's say you have GNU Radio has also incorporates some channel models. You could parameterize these channel models with some data that you already know, that you learned from the guys who were driving around with a channel sounder. You maybe can plug this data in and then do some simulations in GNU Radio and come up with some more realistic error curves that you can then use in your simulator. So maybe these are some applications that are more high layer. Okay, so that's it from my side, and I quickly want to wrap this up. So we have this Ofdm transceiver implemented, and yeah, I hope that it's easy to use, and that's modular and extensible. And yeah, I showed you some possible applications about that. Maybe you can come up with something more. Okay, finally, I have some other projects I'm currently working on. This is RDS, which is decoding radio data service, and also some Zigbee files. I also contributed there. And for these 3 projects, I also have some demo stuff with me. So if you are interested, you can just talk to me, or we can have a look at that if you want. Okay, so thanks for your attention. Yes?
Probably you are aware of the WAVE, the DSRC project.
Yeah.
It's good that they finally standardized the physical layer, but is there some standard coming out for the link layer as well?
So there's ETSI ITS-G5, and then there is this DSRC WAVE, and they both use 11P as the physical and MAC layer on top of that. And both give recommendations on how to use this physical and MAC layer. So it's no definite answer to that. I mean, for example,
over TCP, they're not using TCP at all.
Exactly, yeah. So I mean, you can also run TCP in theory on top of that, but for these traffic applications, you have a different stack for that. Yeah. And there you have quality of service for different traffic classes, for let's say safety or more multimedia streams and stuff like that. So they build up on 11P as the basis. Yes?
Do you think with the next generation hardware you could meet the Wi-Fi specs with pure software radio?
No, not with this approach, because I think if you really want to meet all these timing constraints, you have to move everything, a lot of stuff to the FPGA, and then that basically means changing the whole architecture of
even the operating system.
No, even if you're using the PCI Express, you can't meet the timing requirements. Yeah, look at there's a paper called The Split Mac by George Nitschus that explains why and how he solved the problem. It's a hack where the FPGA sends out a pre-calculated ACK, and then it processes the real packet if the SN, like based on the SNR. It's a clever little hack, but he basically shows you how you can't even do it with PCI Express.
I mean, it's not exactly a question, but if anyone was